Alright, for 1D, we're testing a series for convergence and divergence, or divergence, and we have an alternating series this time. So we have the sum from n equals 0 to infinity, negative 1 to the n times n over the square root of n cubed plus 1. So remember that when you have alternating series, you have a couple of possibilities. It could be divergent. It could be, but there's two classes of convergence. There's absolute convergence and conditional convergence. So remember that conditional convergence means that this converges, but its non-alternating form does not. And absolute convergence means this converges and its non-alternating form also converges. So we're going to need to test both. So first let's just use the alternating series test. So remember that the alternating series test has two things that we have to check. The limit of the non-alternating part of the series is equal to 0. And this means that the series is decreasing. So if those two things are true, and it's alternating series test says that it at least conditionally converges. So let's check these two things. Our series, sans the alternating part, is n over square root of n cubed plus 1. Limit as n goes to infinity, is that 0? That would be yes, because the denominator has a higher degree, or effective degree, than the numerator. Square root of n cubed is bigger than n, because square root of n squared would be exactly n. So if your denominator is larger than your numerator in degree, your limit is 0. Again, something you could show and prove by L'Hopital's rule. Alright, so that part's true. So we need to show that it's a decreasing series. So that means if we choose n plus 1 in for n, that we get always something smaller than we started with. So you want to write out an inequality like so. We want to show, is this always less than or equal to n over, or not always, but at least eventually less than n cubed plus 1. So let's see what happens here when we expand this. So when you expand n plus 1 cubed, you're going to get n cubed plus 3n squared plus 3n plus 1, and we have an additional plus 1, so we get plus 2. This side will leave the same. So let's think about what's happening here. Our numerator, every time we get to the next term, our numerator went up by 1. But our denominator went up by some approximate square root of 3n squared plus 3n plus 1, because all of this stuff got added into the denominator. You can think of adding a 3n squared under a square root is kind of like adding an n, because the square root of n squared has approximate degree of 1. Obviously it doesn't work exactly because you're adding and you can't do the square root of each term. But it effectively is like adding an additional variable. And even the 3n is like adding a square root of n. So we're adding terms that are like getting bigger as it goes by, whereas on the top we're just adding 1. So this fraction is definitely smaller than this eventually, because the denominator is going up way faster than the numerator. So we have that both of these conditions are true. I want to point out that another way that you can prove this is that showing that its derivative is negative. Because if the function's derivative is negative, that means it's decreasing as well. In this case, you have to do a quotient rule and be a little tougher than some of the other ones you have. So both of these things held, which tells us that this series is convergent. But we don't know if it's conditionally convergent or absolutely convergent. We know it's at least conditionally convergent. So to check finally the difference between those two, we need to try the series by itself, meaning non-alternating. So if we had the following series, we're asking ourselves, does this converge? Well, we can kind of use a similar prospect to what we used up here. The bottom essentially has the degree of 3 halves because we're taking the square root of a power of 3. The top has a square root of 1, or has a degree of 1, which means that the difference between them is only half. By p-series, you should be aware that that's probably not going to converge then. We'll show this concretely by using limit comparison tests. So you might be asking, why did I use limit comparison instead of regular comparison? Because if we think that this diverges, we have to show that it's bigger than some other series that also diverges. However, in picking something like you would normally pick like that, without the plus 1, the problem is that this denominator is larger than this one, meaning this is smaller than this, which by comparison test doesn't work, because if we think it diverges, we have to show that it's bigger than something that diverges. And we just showed that this is smaller than something that diverges, so that's not going to work. So instead, let's just use limit comparison test, but we're going to use the same thing. Limit comparison test says that if you take the fraction of your series to the one you're comparing it to, and you take the limit as n goes to infinity, if you get a positive finite number, then these two series have the same behavior. So if you get 0 or infinity, then it's inconclusive. So let's see what happens here. Instead of dividing, we can multiply by the reciprocal. So the reciprocal of this would be that. You can see here that these n's cancel out. And we just get square root of n cubed over square root of n cubed plus 1. These two functions have the same degree. So when you take the limit as n goes to infinity, you would just take their coefficients, which are 1 and 1. So this is equal to 1. So that is a positive finite number, not 0 or infinity. So that tells us by limit comparison test, these two functions have to have the same behavior. We know that the one we were comparing to diverges by p-series because this is, actually I forgot to say that at the beginning. This is n over n to the 3 halves, because the square root of n cubed is n to the 3 halves. That simplifies down to 1 over n to the 1 half. By p-series that diverges because your power is less than or equal to 1. So since this diverges, and in taking the ratio of their limits, we got 1, that means this must also diverge. So, therefore, the series without the alternating part diverges. With the alternating part, we got convergent by alternating series test. So therefore, you would say that this function is conditionally convergent. So conditionally convergent So that was by using both alternating series test and the limit comparison test.